and stuff. I was like, how are you better friends with me right now than everyone in this room?
Oh, sorry.
Okay, so the test was pretty good results.
Oh, I'm an idiot.
Lag.
Nice.
Honestly though, like I thought I usually lag, so I'm not mad about it.
We need a gaming round. Come on, NBA.
Like I
So,
can say
um,
that
I like when you said, what?
hello, the customer.
There were 7 5s and 3 4s. Everybody got a 5 or a 4. That's really, really good. So I'm proud of you guys. You guys are doing great. Okay, so I'll answer any questions you have on the test right now.
Can you just do the last one?
Sure.
Yeah.
The last one was an actual question, a complete free response question from an actual former test. So I thought it was a good, relevant thing. I don't know what's up with this. Smart notebook not responding. I'll use chocolate.
Yeah.
So let me stop presenting. I'll use chocolate.
Number 2 is in the
That's
middle,
right,
and then
that's
four's
right.
math zone, and then there's a circle 4.
I just couldn't say I didn't eat it.
You get it right.
I'm going home. Sure.
Okay, so let me focus the camera here. All right, so
The rest of the week, finish it.
number 9. Okay, so the first question says, let f be a twice differentiable function such that f of 2 equals 5 and f of 5 equals 2. Okay, it says let g be the function such that g of x equals f of x. So the fact that they're telling you that f is twice differentiable, that means that it's continuous and differentiable, and its derivative is also continuous and differentiable, right? That's what that means. If you have a continuous differentiable function, then any composition of that function is also continuous and differentiable. So g is also continuous and differentiable. In addition, any operations on continuous differentiable functions are continuous and differentiable. So if you look at like part C or part D, I have A, B, C, C, I just realized. If you look at the second part C, h of x is also continuous and differentiable because it's operations on continuous differentiable functions. So that's just a fact that you should know. All right, so part A, it says explain why there must be a value C between 2 and 5 such that f prime of C equals -1. This is the mean value theorem straight away, all right? So all you need to do is you need to say f of 5 minus f of 2 over 5 minus 2. This is 2 minus 5 over 5 minus 2 equals -1. You have to show that work, that the average rate of change is -1, okay? Then you can say since f is differentiable, there has to exist a point blah, 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 blah. Remember, what they're looking for when they're grading a question that deals with a special theorem, whether it's the intermediate value theorem, or the mean value theorem, or the extreme value theorem, or Rolle's theorem, or whatever, they're looking for 2 things. They're looking for, do you know that that's what you're supposed to use? And they're also looking for, do you know that that particular theorem applies in this case? So you have to state the fact that the hypotheses of that theorem are actually satisfied in this case. They're going to look for, are you noticing the fact that f is differentiable? The only way that you can prove that is by writing it down, okay? You don't write it down, you don't get credit for it, okay? This might be working now. All right, I'm going to reshare my screen. I think it looks better on the recording. Okay. So part B. Okay. Part B. It says show that G prime of 2 equals G prime of 5. You have to actually show that work. All right. So you'd say G prime of X. Remember, G of X is equal to F of X. Right. So G prime of X would be F prime of F of X times F prime of X. Right. That's the chain rule. And then if you substitute in 2, G prime of 2, you get F prime of F of 2 times F prime of 2, which is really F prime of 5 times F prime of 2. And if you do the same work, plugging in 5, G prime of 5, you get F prime of F of 5 times F prime of 5, which is F prime of 2 times F prime of 5. That's the first part of the question, just showing that those two are equal. Okay, that was worth 1 point. Actually, 2 points. It was worth 1 point, and then, again, I'm getting this like point distribution from the actual rubric that they used when they graded this Regency or this AP exam. Okay, so you got 1 point for correctly finding the derivative of G, and you got 1 point for showing that these two things are equal. The third part of this question says, use this result to explain why there must be a value between 2 and 5 such that G double prime of K equals 0. This is actually the mean value theorem of also, but instead of using the basic function as being F like they did in part A, right? They're using the basic function as being G prime, right? If you have this differentiable function G prime, which we know it's differentiable because they tell us that F is twice differentiable. So if F is twice differentiable, that means that F prime is differentiable. And if F prime is differentiable, then so is G prime, right?
So for that second part, all I had to add was the fact that G prime was differentiable.
Correct. Yeah. So you can either state that G is twice differentiable, since F is twice differentiable, or you could state that G prime is differentiable since F is twice differentiable. Okay, so that's what they're looking for here. You'd say, I'm not going to write it, but you would just say, since G prime is differentiable, there must exist a point such that blah, 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 blah. And the reason why it's equal to 0 is because G prime of 2 minus G prime of 5 over 2 minus 5 is 0. Because G prime 2 and G prime 5 are the same thing. Does that make sense? Yes, go ahead.
So I didn't get any points for these nice graphs. Pretty nice.
No, because remember, all right, so this part B was worth 3 points. The first point was finding G prime correctly. The second part was showing that G prime of 2 and G prime of 5 are equal. The third part was using the mean value theorem, but you don't get that point unless you state that G prime is applicable for the mean value theorem. Like you have to state that concept, the differentiability part of it. Does that make sense? Whenever you use any type of special theorem, you have to state that that theorem applies. In other words, you have to state that the hypotheses are satisfied of that theorem. So if it's the intermediate value theorem, you have to state that the function is continuous. If it's the mean value theorem or Rolle's theorem, which this is actually Rolle's theorem, but you could say mean value theorem because Rolle's theorem is just a special case of that. You have to state that that function is differentiable, okay? If you're going to use the extreme value theorem, you have to state that the function is continuous on a closed interval. Those are the hypotheses that are important, okay? These theorems don't always work. They only work in certain situations. You have to state that you know that fact, okay? Part C says show that f double prime of x equals 0 for all x. Okay, then the graph of G does not have a point of inflection. So the most efficient way to do this is to actually find G double prime, because if you're trying to show that G doesn't have a point of inflection, you really just need to show that G doesn't, or G double prime doesn't change signs. That's really what you need to show, right? To show that a graph doesn't have a point of inflection, That means its second derivative doesn't ever change signs, right? It's not enough just to say, since f double prime never changes signs, then g double prime never changes signs. That's not obvious to me, and it's not going to be obvious to the AP reader. You have to actually find g double prime and show that it doesn't change signs, okay? So if g prime, we already found it, previous problem, is f prime of f of x times f prime of x, then g double prime, it's a product, right? So you gotta use product rule. It'll be the first times the derivative of the second plus the second times the derivative of the first. This would be f double prime of f of x times f prime of x. That's the second derivative of g, but it's 0. Because if you look at it, this is 0, which makes that whole thing 0. And this is 0, which makes this whole thing 0. So g double prime of x equals 0 for all x. Now you can state g double prime never changes sign because it's always 0. So it doesn't have an inflection point. Some people got a little more specific. They said, well, if f double prime is 0 for all x, that means that f prime is linear for all x. And then they like kind of work their way backwards. That argument works. If you're careful about it and you sort of write more, then it works. But I think it's a little harder to do it that way. This is like the most direct way to do it. And in the rubric for this AP exam, this is the way it was done. And they said you get 1 point for correctly finding g double prime and 1 point for your explanation of why there's not an inflection point. Does that make sense? Okay, and then part D, or the second C, C2. It says let h of x equal f of x minus x. And again, this is a continuous differentiable function because f of x is continuous and differentiable, and so is x. And whenever you have an operation on two continuous differentiable functions, that operation is also continuous differentiable. It says explain why there must be a value between 2 and 5 such that h of r equals 0. This is actually the intermediate value theorem. So you have to state the fact that this is continuous, since f is continuous and so is x. And then just find the values. Like if you find h of 2, this is f of 2 minus 2, which is 5 minus 2, or 3. If you find h of 5, this is f of 5 minus 2, which is 2 minus 2. Wait, I messed up.
Minus 5.
Minus 5, yeah. 5 minus 5, this is 2 minus 5, which is negative 3. So since, you have to say like, since 0 is between negative 3 and 3, between negative 3 and 3, there has to be, by the intermediate value theorem. Okay, so again, what they're looking for in this problem, you get 1 point for correctly finding the values of h of 2 and h of 5, and you get 1 point for this part. But to get this point, they're going to look for two things. They're going to look for, did you mention the word intermediate value theorem or actually state what the intermediate value theorem says? And did you show that the hypotheses are satisfied? Did you say that the function h of x is continuous? That's what they're looking for in this problem. If you don't have both those parts, you don't get that point. Everybody understand that? Okay. What else? Yeah.
Can we go over 8, please?
Sure. Number 8 was the optimization problem. And I thought as far as optimization problems go, this wasn't a super hard one. So we have the parabola. This is y equals 9 minus x squared. and you're trying to find the maximum area of a triangle that's like described in this parabola like that. And I did one kind of like this in class with the sine curve. It's kind of like the same idea here. With that was with a rectangle, this is with a triangle, but it's the same idea. So I think the best way to do this is to just label this distance x, because then this distance is also x, right? So the area that you're trying to maximize is 1/2 base times height. 1/2 of base, which is 2x, times the height, y. And the relationship, like if this point has coordinates x, y, then the height is really just 9 minus x squared. So this substitution just goes in for y, and that's it. So you have area equals, the 1/2 and 2 cancel, so you get x times 9 minus x squared, which is 9x minus x cubed. And then it's helpful, I think, to just realize that there are endpoints here, like x has to be somewhere between, in order for this to work, x has to be somewhere between 0 and 3. Right? This is 3. This is -3. Like you could have a short little fat triangle like this that's really close to 3, or you could have a triangle that's super tall and like that, that's where x is really close to 0, but it can't be equal to 3 and it can't be equal to 0 and it can't be outside that interval, right? This is important because when you go to do your first derivative test, like you got to know that there's boundaries to what you can test. You can't test 4 in there. It's not going to work out because it's not, in this application, it's just not in the domain. All right, so then first derivative test would be the easiest, most direct way to do this. A prime would be 9 minus 3x squared. Set it equal to 0. 3x squared equals 9. So x equals plus or minus radical 3. Now, in the context of this problem, it has to be positive radical 3, right? So then you do a little first derivative test to make sure that that corresponds to a maximum. Like you don't know just by looking at this. I mean, you kind of know, but you have to prove it. You don't really know that radical 3 corresponds to the point where the area is a maximum. It might be a minimum. Maybe the maximum occurs at one of the endpoints. I mean, you kind of can tell on the picture that's not true. But you got to show the work. Like you have to prove to the readers that you're taking into account endpoints and that you're taking into account that this could be a minimum. But you have to show that, okay? So radical 3, this ends up going positive, negative. So that's definitely a max. Now you can state that the maximum area occurs at radical 3, since A prime changes from increasing to decreasing, or from positive to negative at that point. But then answer the question. The question says, what is the maximum area? So now you have to substitute radical 3 in. So A of radical 3, this would be 9 radical 3 minus radical 3 cubed. And you can just leave it like that. You don't have to get a decimal or anything like that. If you do get a decimal, it's 10.392, but you don't have to get a decimal. You can leave it just like that. So in this question, it was worth 8 points. There was 2 points for setting up the objective function correctly, 2 points for correctly taking the derivative, setting equal to 0, and solving, 2 points for doing the first derivative test and accounting for endpoints and things like that, and then 2 points for the correct answer. That's the way I split up the points. This wasn't an actual AP question. This was just a question I made up, but that's the way the points were split up in this case. So you know, like what you had to do to earn the points. Like those are the things you had to do. So like for example, if you didn't include this part and you just had this work, you got 2 points off because the first derivative test was 2 points in this question. Does that make sense? And I'm trying to split up points like they do on the AP test, which is questions or parts of the question that are more work or more important work are worth more points. It's pretty logical to do that, right? Like if they say use correct units, they're not going to give you like 4 points for using correct units because that's just a tiny little thing, right? So that's kind of the way that they decide points. How much time does that take and how important is the idea? Okay, what else? And just another thing about that, just test taking strategy. Like if you think about that on every question, like what's the most important part of this question, and spend your time on that, that's like getting like the most out of your time, you know? Like if you gotta leave something blank, don't leave a part blank that you think is worth 5 out of 9 points. That's like a bad idea, right? You wanna get some work down so that you can at least earn some of the points there. And you'll see, like, as we do more of these problems, like the types of things they give points for and how many points they typically give for those types of things. Like sometimes you can get like 2 or 3 out of 9 points just for like taking the derivative and setting it equal to 0, which is something like you do in almost every problem, right? That's what we've done like in almost every problem, taking the derivative and set it equal to 0. So even if you don't know what to do, take the derivative and set it equal to 0. Maybe you'll get 2 or 3 points. You know, I mean, even if you're totally clueless, like play the game, just do something, you know? Yeah.
So like, for example, for 7, obviously it says in the question that it's worth 7 points total.
Yeah.
On the AP exam, it doesn't tell us what each part is worth, so
Right.
it's all, we just have to guess.
Yeah.
Okay.
Yeah. So, and they're all worth 9 points. Every AP question, free response question is worth 9 points. So, but as we go through the different types of questions, I'll share with you the rubric of how much it's worth, and you'll get used to it. Like you'll be able to tell me soon, like if it's ABC, this part's worth 2 points, this part's worth 4 points, and that part's worth 3 points. Like you'll figure it out because it's very standard and they're like very consistent year after year. Okay. Any other questions on the test? Okay. Well, like I said, this is you guys are doing a really, really good job, and I'm really confident that everybody's going to do really well on the AP test. So you guys should be too. Okay. All right. So we're going to start a new topic. The way that this is going to work in the next couple weeks, we're going to start talking about basic integration. We're only going to talk about it for a few days, and then next week we're actually going to take a cumulative test on units 1 through 5. So it's going to be almost like a practice AP test over 2 days. The first day you're not going to be able to use a calculator, and the second day you are going to be able to use a calculator. And I got all of the questions, I mentioned this last week, but I got every question on this practice AP exam off of a single AP exam. So it's like there's a wide range of question difficulty. Unlike normally, I try and pick like all the hardest questions for your test. This is going to be more like an actual AP exam where there's actually some questions that are pretty easy and some questions that are kind of hard. It's going to be a good indicator of like where you are like overall. Okay, so that's the plan. Next week it's going to be on Thursday and Friday. Thursday, which the date is the 17th. So Thursday the 17th is going to be no calculator. Friday the 18th is going to be with a calculator. And this is going to be just like 2 like normal tests. So I'm just going to count it as 1 though. Okay. So that's the plan. But before then, I'm just going to start talking about integration a little bit, which is what Unit 6 is about, techniques of integration. And then when we get back from break, I'll kind of review that, and we'll start in Unit 6 like more seriously. Yeah.
So is next week the last week before break?
There's like a Monday and Tuesday,
Oh, okay.
but on the Monday and Tuesday before Christmas, we're just going to go over the test, and I'm going to talk about. There's actually a little bit of work I want you to do over break, but I'll give it to you on Monday so you can start early if you want. Did you have another question?
No, I chimed in when I said play games.
Oh, it's a possibility, or you might want to start your break homework. It's up to you. Yeah.
Pearl, on our cumulative test, are we going to have an introduction stuff?
Great question. Possible. Yeah. The stuff we do in the next couple of days might be on Thursday and Friday's test. I think there is like 1 question, maybe 1 question. And then your break homework, there's also, I think, 1 question that deals with integration. Anything else?
Wait, so when it comes to the actual like AP exam, does it tell us what question we can and can't use calculators for? Or
The actual AP test, yes.
Okay.
It's like, the first 45 minutes of the test, you're not allowed to use a calculator, you have to put them under your desk or whatever. And then they give you your calculator and you can use it for the next 45 minutes. And then same thing with free response questions. You get your calculator for the first half hour, and then they take it away for the next hour, I think, because you get 15 minutes per question.
so it's kind of split up the same way like an SAT is where there's like sections.
Yeah.
Okay.
Yeah, and like, as we get closer, I'll reiterate this, but on the free response questions, like, you're allowed to use your calculator on number 1 and 2, and you're not allowed to use your calculator on number 3, 4, 5, and 6. But there's a strategy involved because you're still allowed to work on those questions, like number 1 and 2, after they take your calculator away. So one thing that I tell people is like, look at numbers 1 and 2 and do everything you need to do that requires your calculator, because anything you have to write, like an explanation or anything like that, save that for when you have more time. Like, use your calculator when you have your calculator, and then when you don't have your calculator, you can still work on those questions. So that's just a strategy thing that we'll talk about when it gets a little closer. But yeah. Anything else? Okay, so today we're just going to talk about something called anti-differentiation, which doesn't mean you're against differentiation. It means like undoing differentiation. So the idea here is, what if instead of giving you a function and saying find its derivative, what if I gave you the derivative and said find the function? That's the idea, right? So if I said, if dy dx is equal to, for example, like 3x squared, then what's y? So this would be an easy one to answer. What's the answer? Okay, kind of. It's a trick question. So yeah, y is x cubed is one possible answer, but there's lots of possible answers, right? There's lots of different functions that have the derivative 3x squared. Who can give me another one? X cubed plus 1. Or x cubed minus pi. Or x cubed plus any constant c, right? This could be any constant at all. Right? Because the derivative of a constant is 0. So if you're trying to find a function that has a particular derivative, that function could be lots of different functions. In fact, an infinite number of functions have that derivative, right? But they're all kind of like the same family of functions. Okay. Now the shorthand notation, like you don't want to write this every time. If dy dx equals 3x squared, what is y? That's like a lot to write. So there's shorthand notation for that, and the notation for it, this whole thing, this is shorthand notation, is it looks like an elongated S, kind of looks like this. Okay, like if this was like typed text, it's like bigger than like the line of text, it's taller. So 3x squared, and then dx. Okay, that's the notation. The dx is necessary more for like when you're talking about multivariable calculus where there's x's and y's, and this is sort of to tell you what variable you're dealing with. Just like when you have dy dx, the dx is kind of telling you what variable you're dealing with. It's kind of the same concept here. The dx, just think of it as part of this symbol. It's necessary to have it there, You can't not have it there, but it doesn't really do anything, okay? So this is sometimes called, so you would say this is equal to x cubed plus c, you would say in this case. And so this symbol, together with the dx, like all together, that whole thing, is sometimes called the indefinite integral. Indefinite integral. Okay, it's indefinite because we're not sure exactly what function has that as its derivative. There's lots of them. It's indefinite because there's this plus c. We'll talk about definite integrals. That's something a little bit different later on. And that's what your calculator can do. Your calculator actually evaluates definite integrals, not indefinite integrals. Just like your calculator will find numerical derivatives, which means derivative at a particular point, but it won't find the derivative of a function. It's the same idea. Your calculator won't find the integral of a function, but it'll find the definite integral of a function, okay? All right, so if this symbol just means, okay, an indefinite integral, you can also just think of that as an antiderivative. The antiderivative. It means the same thing. And technically, I really wouldn't say the antiderivative because it's not unique. I'd have to say like an antiderivative, right? Instead of the antiderivative. But if this process of integration is just finding an antiderivative, then doesn't it make sense that if we have all these rules for finding derivatives, we could just kind of reverse them to find rules for finding integrals? Well, that's the way it is. It's exactly like that. So using rules for differentiation, we can find rules for anti-differentiation or for integration. Okay, for example, like we have this rule that says that the derivative of a constant times x is equal to the constant. That's true, right? Like the derivative of 2x is 2. So the corresponding integration rule would be the integral of a constant would be the constant times x plus c. And now I shouldn't even use c. But they're different c's. This one's capital. This is not the same c, right? This c is like fixed. This c is like any constant, and any constant will do. Okay, so you can see, I mean, I just took a standard like differentiation rule that's super easy that we know, and I made an integration rule out of it. So if you ever see something like the integral of 5, the answer is 5x plus c. Now, can you forget the c? Yes. Should you forget the c? No, because they'll mark it wrong. Okay, if it's multiple choice, they'll never have it without the c. But if it's free response and you have to give an indefinite integral as an answer and you forget the plus c, they'll take a point off for that. So don't forget that. It's kind of important. Okay? Or if I had the integral of pi, the answer is just pi dx. Or pi plus c, rather. Another thing that's important that the dx is there for is like, what if you had something like the integral of 7 dt? The answer would be 7t plus plus c, right? Because t is the variable that you're working with in this case, right?
Would it be pi x plus c?
Yeah, I messed up. Thanks. Thank you. Okay, so that's the first integration rule. The derivative or the integral of a constant is the constant times x. It makes super sense, doesn't it?
Yeah.
All right. Let's just do one more rule. Let's do the power rule. The derivative of power is n times x to the n minus 1, right? So if we try and like reverse engineer this into an integration rule, and I try to take the integral of x to the n, the answer is, I'm going to write it down and then we'll just make sure that it makes sense. It's x to the n plus 1 over n plus 1 plus c. So if you ever want to check an integral to see if it's right, you can always just differentiate and make sure you get that, right? That makes sense. Differentiating an integral should give you like what you started with, right? So you can check this pretty easily. If you try and take the derivative of this side, in other words, the derivative of x to the n plus 1 over n plus 1. Well, the derivative of this first piece, the 1 over n plus 1 is just a constant multiple. The derivative of x to the n plus 1 would be n plus 1 times x to the n, right? Because you subtract 1 from the exponent. And those cancel. So you can see you definitely get x to the n plus 0. So it checks out. When I differentiate it, I get x to the n. Does that make sense? And it kind of makes sense intuitively too. Like if you are multiplying by n, which is this exponent, and then subtracting 1, it makes sense that you should add 1 and then divide, right? The opposite of multiplying and subtracting 1 is adding 1 and dividing. So that's kind of what you're doing intuitively, and it makes sense. Okay, all right, so we'll pick this up tomorrow and talk more about the rules for integration, and that's it. But again, really nice job on the test. Keep it up. You guys are doing really good.